So we are back again, and in the second part we shall prove this theorem here, give the main ingredients to prove that given a G manifold, namely a manifold with an isometric action by a compact Lie group, then given any smooth G invariant function on the manifold, if there is some C such that this inequality is satisfied, then this function f, that is G invariant, can be prescribed as the scalar curvature for some G invariant remaining metric on the manifold. And what are the main ingredients before going back to the slide that I just skipped? Let me state the general procedure. Let's consider by f the function that takes some metric on the manifold and return its scalar curvature. For instance, if we take a metric g, then we consider by fg as the value of as the function that represents its scalar curvature. From now on, we have a closed Riemannian manifold fixed with some initial metric g. Okay. Then let's consider a linearization of this operator f, but on this very point g here that we fixed. And from now on, we fix this initial metric on the manifold. So by taking the linearization, that's nothing more than just taking this derivative here, it will give rise an operator from the space of matrix to the linearization of the space of functions, that is the space of function. So this operator A, it maps a metric to a smooth function, and it has the following expression here in coordinates, where Rej is simply the components of the Ricci tensor of the metric G. Okay, so we have this expression for the linearization of this operator that takes a metric and returns its scalar curvature. A is just the linearization of this operator on the point G that we had fixed from now on. Okay, and then we can take this formal L2 adjoint that has this expression here, and it can be verified that this adjoint, this operator, is elliptic. So we are trying to use elliptic theory to understand which smooth functions can be prescribed as the scalar curvature for some G invariant matrix, and the inequality that shall gives us the result is this one that is obtained by the mean of elliptic theory. So let's move on and see how it goes. We have this first lemma here that states that if the kernel of the adjoint operator is 0, except possible if the scalar curvature of the metric that we just fixed is either a positive constant or it's a zero constant, but a zero constant that descends from an Einstein metric with zero Einstein constant. Namely, our initial metric is an Einstein metric with zero constant, or in other words, our initial metric is H flat. Okay? And moreover, we have that if the kernel of A star is 0, then the map that takes a metric here, we're considering the Sobolev space of metric, and then mapping to the LP space, that is nothing more than just this expression here understood in the weak sense. So this operator is a surjection. Okay, we have first that the kernel of this operator is always 0, except if the scalar curvature of our initial metric is a positive constant, or if our initial metric is H flat. And then we also know that if the kernel of this operator is 0, which is the case if the scalar curvature is not a positive constant, or if the metric is not Einstein, then this operator is a surjection. As a second lemma, we have that, well, assume now that P is greater than N, and assume that A star is injective. Then the functional f, that's the operator that takes a metric and maps to the scalar curvature of this metric, is locally surjective. So here we have that uh, the kernel of this operator A star is trivial on large classes of cases, and when it's trivial, then the linearization of the operator is a surjection. And here we have that if the kernel of this operator is zero, then the function, which A is the linearization at some point, is locally surjetive. And then how do we prove our result? We need the following. We need the last ingredient, that is called the approximation lemma. If we take two continuous G-invariant functions on a manifold in a way that the image of this function h is contained in the image of the function f, then for each epsilon greater than 0, we can choose a basic diffeomorphism phi on the manifold from the manifold to itself, such that up to composing f with phi, f and h are LP close as we wish. And what do I mean by a basic diffeomorphism? I mean that if we restrict phi to an orbit of G on the manifold, then it has constant value along all the orbit. Okay? So we have these ingredients, we have this approximation lemma, we have conditions in a way that A star is injective, and also we know that when it's injective, then it's also a surjection. Then A is a surjection, and we have that for p greater than n, then if the A star is injective, then indeed the function f is locally surjetive. The operator that takes a metric and maps to the scalar curvature is surjetive. Well, so what do we do? Consider any smooth G-invariant function satisfying this inequality here. So C times F has the property, will play the role of F here. And the scalar curvature will play the role of H. Okay? So we have this inequality. Then, by the approximation lemma, we know that up to some basic diffeomorphism, C times F is arbitrarily close to the scalar curvature. Okay? We do know this. But then, since we started with some arbitrary metric, we can make some G-invariant perturbation of this metric such that this inequality would be also satisfied, but perhaps possibly with not being strict anymore. So we consider our initial metric in a way that this inequality is also satisfied, but with the possibility of the inequalities not being strict anymore. We consider this change, and in a way that the scalar curvature of this deformed initial metric is not a positive constant, nor hit flat. Okay? Then we do know that the kernel of the linearization at this point of this metric is 0, but then the operator is surjetive. Okay? Great. Since the operator is surjetive, and the kernel is injective, then this f here is locally surjetive. Okay, and now we are on all the hypotheses of the inverse function theorem on Banach spaces, and then it means that on a neighborhood, on a very small neighborhood, LP neighborhood of the initial metric that we just started, we can realize the function. So since this function here is arbitrarily close to the scalar curvature, this function here is on this neighborhood of the metric. So we can realize it as the scalar curvature because we can find some metric such that f of such metric is precisely C times f composed with phi. And then we just take this pullback here and we could realize the function f as the scalar curvature. So this is how it goes, the theory. And to give some applications on the exotic spheres that was intended at the beginning, I would like to mention that Carlos Duran and Esperança myself approached the problem of systematically constructing diagrams such as this to realize exotic manifolds. But what do I mean by this diagram? Here on this column, we have some principal bundle P with total space P, basis M, and structure group G. Naming this column here is a principal bundle, but we with principal action bullet. But do we assume that we have another action that we denote by star and another principal bundle here on this line? And then we assume that the action star and the action bullet, they do commute. I claim that it's possible to construct to show such diagram in a way that M is a classical sphere and M prime is an exotic sphere. For instance, we can consider this diagram here. We take sp2, which I recall very soon, and with structure group S3, and give two actions such that the quotient here is the standard 7 sphere, and this is the standard Gromov-Meyer, is the Gromov-Meyer exotic sphere. Okay, so let's see how the construction goes in this case. Well, I just recall that sp2 is the group of quaternionic matrices on the plane that preserves the natural inner product on the hyperbolic plane. Okay? So each line here is quaternion, and more interesting, each line defines an element of S7 when S7 is seen inside the direct descent of two quaternionic planes. Okay, that is homeomark to R8. Okay, good. So now we have as bullet action simply this action here that consists on multiplying by right multiplying the right column on the matrix uh, of sp2 by this key bar here, where key bar is an element of S3 and therefore it is an unitary quaternion. Okay, so key is just a unitary quaternion, and then we take its conjugate and just multiply it here in this manner. So the projection onto the first column defines the first the first principal bundle here with this bullet action being by multiplying by this key bar, and as quotient we obtain a 7. So Gromov-Meyer introduces the star action that is a little bit more complicated, and as you can see it commutes with the bullet action, and there is if you take the quotient map according to this action, we obtain the Gromov-Meyer 7-dimensional exotic sphere. So this is an example of such a diagram. Okay, and things can be as complicated as you want. For instance, by pulling back star diagrams, we can realize another construction to obtain M to be the standard 8-dimensional sphere and M prime as the only 8-dimensional exotic sphere. Here is it is explicitly written the map to pull back, for which by the means of the pullback we can construct the associated cross diagram. Okay, so we have this theorem that says that, well, since the actions star and bullet are commuting on P, then when we take the quotient M prime, the action bullet defines a non-trivial action on M prime. Same manner, star defines a non-trivial action on M. Okay, so it does make sense to see M as a G manifold with star action and M prime to be a G manifold with bullet action. Okay, so let's move on. And then our theorem says that, well, it's a property of this star diagram's construction that any star invariant function f here give rise to the same function on M prime that is bullet invariant, because basic functions here are constant according to the star action. So they can be lifted here just by composing with this projection. And then we can just project it once more, since this lift here is both star and bullet invariant. So we have that the same G-invariant functions here according to the star action can be seen as the bullet star invariant functions on M prime. And our theorem says that any star invariant function on M is the scalar curvature for some star invariant metric on M, and up such an identification, it is also the scalar curvature of some bullet invariant metric on M prime. In this manner, S7 and sigma 7 admit the same S3 invariant functions as scalar curvature. And moreover, S8 and sigma 8 also admit the same invariant functions as scalar curvature. Therefore, in the presence of symmetries, the same invariant functions are admissible as scalar curvature on both classical and exotic manifolds, indicating that symmetries mitigate exoticity. As some further results that we obtained just as consequence of the machinery developed, we have the following, that is unreached theorem. Suppose we have that manifold with an isometric action, and we assume that the manifold do not admit a metric of positive constant scalar curvature. Then the Lie group necessarily must have an abelian Lie algebra, and any metric that we take on the quotient cannot have positive scalar curvature. We also conclude some density results. For instance, on a Riemann manifold with an isometric action by a Lie group, and assume that the action is semi-freely, meaning that it is free almost everywhere. Okay, it's free almost everywhere, but where it's not free, then the isotropy group is discrete. Okay, then assume that G has non-abelian Lie algebra and let F be any smooth function. Okay, then there is a metric G tilde that is the scalar curvature of F, which is arbitrarily LP close to a Tigger deformation of this metric. Okay, so every realizable function can be realized by a metric that is arbitrarily close to a metric that is a Tigger deformation. And to the people that work with positive curvatures, this is interesting because Tigger deformations has the property of increasing curvatures. Okay, so it's a natural tool to promote positive curvatures, such as Ricci and scalar curvatures. So this shows that such deformations they are somehow dense in the set of realizable scalar curvature functions. Okay, so the scalar curvature of Tigger deformations are dense in the set of realizable scalar curvature functions. Okay, and just to finish, I would like to very briefly say that we obtained a result on how to prescribe scalar curvature on trivial products of manifolds, also by variational methods. I shall skip this slide here just in order to save some time, but when you are reading the slides that you just left on the available to you to read, and if you have any question, please ask me. But I would like to state this result here because it has an important corollary that says that if you have a closed enlargeable spin manifold, by enlargeable, this is a very natural concept on spin geometry. And for instance, if you want, you can think that you have a torus, for instance, just to clarify your feelings. And assuming that we have a Riemann metric that has positive average scalar curvature. Okay, so we take a torus, for instance, and a metric on the torus that has positive scalar curvature on average. Okay, so we assume this. Then the first positive eigenvalue of the Laplacian on this metric satisfies this follow inequality here. That we believe that is quite interesting because upper bounds for the first eigenvalue of the Laplace are assumed under stronger conditions such as bound on the curvatures. Here we do not assume any bound, just positivity of the average of scalar curvature. And here, of course, we are on the dimension greater or equal than 3, just because this would not be possible by the Gauss-Bonnet theorem on dimension 2. Okay? And just to finish, I would like to say that Professor Esperança and I, and also Professor Duo, we obtained as consequence of this work answers to given a Riemannian submersion. We prove that if the fiber has a metric of positive scalar curvature, then any smooth function defined on the total space of the submersion is the scalar curvature of some Riemannian metric. And more recently, Professor Marcos Alexandrino and Gustavo Ramos, a PhD student, fully developed the concept of Sobolev space of basic functions on singular Riemannian foliations. This is a paper that's going to be online very soon. And we prove analogous results, for instance, such as the generalization of the larger embeddings that are used on the stock in the scenario that the foliation is not induced by the orbits of a group action, but just partitioned by submanifolds that are locally equidistant. We also provide an analogous principle of symmetric criticality that we just used from Palais, and to obtain the results in the lines of Kazdan-Warner. And this approach will allow us to work with physical problems in the scenario of manifolds with foliations, for instance, Schrödinger equation and another two problems. And just current questions that I intend to approach in the near future are: do symmetries mitigate the obstructions for rich tensors? Namely, if we assume that the rich tensors are invariant by some group, and considering the star diagram realization, can one prescribe the same rich tensors on both classical and exotic manifolds? And also, as a more naive question is, well, since Sobolev spaces and the regularity theory depends on smooth structures, can smooth structure obstruct positive can smooth structure obstruct positive sectional curvature, and can this be seen by the means of regularity theory of PDEs? So with all of this, I finish my talk. I hope that you have enjoyed. Thank you very much.